So yeah, hello everyone. A very good evening to one and all of you. I hope I'm audible and visible. If not, any one of you can confirm it. So let's wait for 5 to 10 minutes so that everyone can able to join this session. Hello. Hello. Yeah, Anis, can you confirm me? Are you able to see my presentation? Hello. Yes. Hello. Anyone can reply? Can you able to see? And
Hello.
my presentation. Yes. Can you confirm it? Are you able to see my presentation?
Yeah, ma'am. It's visible and it's audible.
Okay. Okay. Thank you. Yeah. Okay, let's start the session. So, hello everyone, my name is Pooja Verma. I'm PMR Research Scholar from IIT Kharagpur, and instructor for this course is Professor Syamal Kumar Das Mandal, Advanced Technology Development Center, IIT Kharagpur. This is a week 7 live and interactive session on signal processing techniques and its application. So, you can use chat box for asking and interacting. So I hope all of you have gone through this week video lecture. So first we will go through some conceptual and theoretical concepts. Then we will solve some problems which will be very similar to your assignment problem. So it may be help to solve your question assignment problems. Okay, so these are the course content for this week. Uh, Course content is fast Fourier transform algorithm and spectrum and spectrogram. So first Fourier transform. So the first Fourier transform is an algorithm that is used for computing the discrete DFT, discrete Fourier transform and its inverse. So the DFT transform are discrete signals into a time from a time domain signal into a frequency domain that allows to analyze the signals in the signals frequency component. So as we know that the for computation, a direct method DFT requires n square complex multiplications and n minus 1 complex addition and total 4n square real multiplications and 4n minus 1 real additions. Okay, so direct computation of DFT is basically inefficient and it cannot be used when we use a large sequences as well as it does not exploit the symmetry and periodicity properties. So FFT is an algorithm to convert time domain signal to a DFT frequency domain efficiently. So fast Fourier transform is an algorithm. Okay, it is not a method. So basically, fast Fourier transform consists of two methods. First one is a divide and conquer approach, and the second one is a that radix to FFT algorithms. Okay, it can be any radix 2 or 4 or 8 also. Okay, so first we will see divide and conquer approach. So as we know that this is a equation of DFT. Already we have seen that that is represented by this form or before that n is equal to 0 to n minus 1 x of n e to the power minus j 2 pi by n k n. So this part here we can write it in this form also wn kn. It is written in this form. Okay, so that is written here, this one. So wn it represents e to the power minus j 2 pi by n. If here putting kn, so it is multiplication of that. Okay. So let sequence x of n has a n number of samples. This sequence has a n number of samples, and that n number of samples we can write in any way. So here we are just that n samples, uh, we are just divide it into L into M form. For example, if n we have 8, right? So we can divide it 2 into 4, right? 4 into 2 also 1 into 8. So here this we will represent in form of matrix in divide and conquer approach. Okay, here this one is a row, this one is a column. Okay, so if now x of n can be sorted in either one dimensional, this x of n we can sort out either one dimensional array indexed by n or two dimensional array. that two-dimensional array indexed by L into M, that is row into column. Okay, so here L will vary, L small l will vary 0 to capital L minus 1, and the small m will vary 0 to capital M minus 1, where L will be the row index, that is 2, and M will be the column index. For example, in a matrix that is we say row, L is the row, M is the column. So M will vary to small m, M minus 1, that number of rows, and L will vary capital L minus 1. Okay. So here in divide and conquer approach, we have to do this mapping. This row and column can be a two ways. First one is this one, capital M, L plus M, either that can be row mapping or can be a column mapping. Okay, so here we are taking this type of, these are the two mappings, can be either row mapping, either column mapping. So that row mapping is represented by capital M, L plus M, and the column will be the L plus capital L M. So if x of n is mapped to a rectangular array, that is x LM, and xk is mapped into corresponding regular, that is it is a time domain signal, and that xpq is a frequency domain signal. It is a two-dimensional signal. Then mapping can be performed either this way or either this way. So this is a frequency domain representation of that same signal, where here it is a two-dimensional signal, that is first one is a row, sorry, this is a column, this one is a row. Okay, for both. So we have to solve for frequency domain both row wise and column wise. Okay, so here correspondingly we will arrange this one. So while we are mapping, what will be the total complexity to solve this type of problem if we are using the divide and conquer approach to solve the DFT problem? The total number of multiplications required, that is this much, M L in brackets M plus L plus 1. So we will use these formulas while we will solve the problem. And total number of additions that is required, that is LM M plus L minus 1. Okay, while in DFT when we are solving the direct formula, so there we have seen total multiplication we required, total multiplication is n square, and addition n minus 1, we have seen that. So for divide and conquer approach, if we are using that much of multiplication and that much of addition we will require. Now how we will, there are two algorithms will be there for both either row wise or column wise. So already you have seen in this presentation slides or materials. So first what we will do in algorithm is store the signal in column wise. Okay, if there is any signal in two dimensions, so first we will store the signals in by a column wise, then compute the m point DFT to each row, then we have to compute the DFT for each row, then multiply the resulting array by a phase factor W, that is W n kn. This is called a phase factor also it is called. Then we need to follow these steps. Okay, if it is given to solve any problem using the divide and conquer approach. Okay, then compute the L point DFT for each column. We have to compute the N point DFT for each column. Then read the resulting array row wise. Then we will read. And similarly for the second algorithm, here we are storing the signal column wise, but here we will store the signal by a row wise. Then similarly just opposite of that, then compute the L point DFT of each column, then we will compute the EDFT, then we will multiply a phase factor, then compute the M point DFT of each row, then again we will compute the DFT of each row, and then we will read the resulting array column wise. Okay, So these are the two algorithms for divide and conquer approach. So basically it will not use the by for the calculation mostly. It will use the computer. It will be used by the computer. Theoretically, we have to calculate all those things, only complexity, and for that to calculate the DFT, we will use mostly FFT algorithms. Okay, this is the most used algorithm to calculate the DFT of any signal. So the radix to FFT algorithms are also a two types. It is either the decimating in time or decimating in frequency. Okay, so first we will see decimating in time or decimation in time. So what we are doing here, decimation in time. So if we have endpoint data sequence, so that endpoint data sequence can be divided by a two parts. It is divided by a two parts. So let's see if we have a data sequence, let's x of n, then we splitting this data sequence in two forms. That is, first we will see f1n and f2n. Okay. So one is a event sequence, and another one will follow the odd sequence. Okay, odd number of values. Okay, so even number and odd number. So here theoretically we can represent the even number by f1n, that is f1n x of 2n, x of 2n. That odd sequence is represented by x2n plus 1. It is in general. Okay, and just a minute. Yeah, sorry for the interruption. Just, okay, so f1n and f2n are obtained by decimating x of n by a factor 2, and hence resulting FFT algorithm that is called decimation in time, because they are whatever sequence is given in time domain, just decimating that fact. That's why it is called a decimation in time or decimating in time. Okay, so total number of complexity that is required for this FFT algorithm decimation in time, that is total number of multiplication required by n by 2 log 2 n. Okay, and total number of complex addition that is required n log base 2 n, that is the complexity of the FFT algorithm. FFT algorithm. So we will just follow this procedure. Just divide the endpoint sequence into two parts. Then we follow even and order sequences. Now, how we will solve the decimation in that? We will use the butterfly diagram. So this diagram is called a butterfly diagram. Okay. So here 8 n is equal to 8 is there. So 8 points we have taken. So here you can see that just we here the lower part is odd part, right? And upper part is even part. So that even part also we have just ordering the descending order. First we will divide this one is that 8 sequence in even and odd part. Then for example even part is 0, 2, 4, 6, and odd part is 1, 3, 5, 7. But here we will give the input in the reverse order here, because we are decimating in time. So just we need to decimate this. So first we will write 0, then 4, just gap up, then 4, then 2, then again 6. Similarly for odd part also. Okay, so this is called a decimating in time. That's why it is called decimating in time. So what we are doing in butterfly diagram, this is a phase factor. All these things are phase factor. The phase factor is multiplied by the lower part. Whatever butterfly we are making, just multiply by the lower part. But in DIT, we will multiply this one, the lower part, but before the this butterfly diagram. Okay, so here w8, here the it will be the 8. Okay, 0, then just add here, for example, x of 0 plus w80 x of 4. Similarly here, what will be the output? X of 0 minus, because here we are multiplying the minus 1 in the lower part. So x of, yeah, x of 0 here, that minus that x of 4, and just multiply this space factor here, w80. Similarly here we will calculate like this, then again we will make pair of 4, group of 4, this 4, again 4, then with all the 8s we will make, then here we will get in the same order 0 1 2 3 4 after. So that's why DIT, decimation in time, is called, the input is given to the reverse order and output we will get the in the same sequence. Okay, so here n is equal to 8 is there, so where these stages will, how we will calculate how many stages will be there. So 8 will be written as a 2 to the power 3, so that represents the three different stages. Okay, stage 1, stage 2, stage 3. Okay, that's, from here you can calculate how many stages you will require. Now next one is, that was a decimation in time, DIT, right? DIT FFT, and this is called a DIF, decimation in frequency, DIF. So in DIF it is opposite to the DIT. Here the input sequence we will give the same order, not a reverse order, same order, but it is opposite to a DIT, because here we are converting, yeah, it will be the in the opposite order. Okay, so here just it is opposite, that there butterfly diagram we are giving in the last, but here we are taking first just opposite, then, but here what we are doing here, the phase factor will multiply after this calculation, after all those things, then just simply we will reduce that. Okay, then but here the output will be the in reverse order, output will be the in reverse order, just remember that, and all those things are similar. Okay, now next one is a spectrum and a spectrogram. So similar, basically spectrum and spectrogram are the tools that is used in the signal processing, but they have different purposes. So spectrum is a signal, the spectrum of a signal represents how its energy is distributed across different frequencies. Okay, how the energy is distributed across the different frequencies. So basically it is used for Fourier transform. It, it will use the first Fourier transform. It is a one-dimensional plot with frequency on the axis and amplitude on the y-axis. So a power spectrum of a sound signal shows the frequency are the most, which frequencies are the most prominent. It is used for that. And a spectrogram is a time dependent representation of a signal's frequency continent. So it basically applies the short time Fourier transform to analyze the how frequency components evolve over the time. Okay, so it will use the two-dimensional or three-dimensional plot with the time of x-axis, frequency on the y-axis, and the color intensity represents the amplitude or power. So a spectrogram of a speech can show how different phenomena have varying frequency content over a time, how the different phenomena varying frequency content over a time, while the spectrum will calculate the energy distribution over the different frequencies. So this is a basic of a spectrum and a spectrogram. So these are the topics which have been covered. Now we will move to the questions that may be helpful to solve your assignment problem. Okay, so question number 1 is, which of the following is true regarding the number of computations required to compute an endpoint DFT? So option A is n square complex multiplications and n minus 1 complex additions. Option B is n square complex additions and n minus 1 complex multiplications. Option C, n square complex multiplications and n plus 1 complex additions. And option D is n square complex additions and n plus 1 complex multiplications. Which option will be the correct one? So already we have seen in the previous slide. So can you tell me normal calculation of DFT, how many complex multiplications and additions are required? Can you answer in the chat box? Any one of you? Please try for at least this basic questions. Yeah, option A. Okay. Yeah, correct one, Anish. So how? So as we know that how we are calculating the endpoint DFT, the endpoint DFT can be calculated by this equation, right? X of k, n will vary, n is equal 0 to n minus 1, x of n e to the power minus j 2 pi by n k n. So here what we are doing, just 0 to n minus 1 till n minus 1, we are, that is n number of, here just first we will take this one, then we will multiply this by this one. So this one is also till n number of factor, because here also n is there. So total n multiplications are here and total n number of multiplications are here. Okay, so total number of multiplication we require n cross n, that is n square complex multiplications are required. Similarly, so after multiplication there are how many number of sums are there? So total n, first just multiply, then add, multiply till n minus 1. So n into n minus 1 complex additions are required. Okay, so to perform n point DFT, total n square complex multiplication, and n minus 1 complex additions are required. So yeah, option A is the correct answer for this question. Okay. Okay. Moving to the next question. So in radix 2 FFT, if the number of points n is equal to 16, then number of complex additions and number of complex multiplications are respectively. So for radix 2 FFT, how many, if n is given n is equal to 16, how many complex additions and multiplications are required? Can you answer for this question? How many complex additions and multiplications are required? Okay, first we will see the formula for radix 2 FFT. Number of complex, first, okay, additions is equal to n raised up to n. Already we have seen that. Okay, So total number of complex additions are that much of required, and total number of complex multiplication that is required equal to n by 2 log base to n. So now you can calculate it. N is given, n is equal to 60. Can you calculate and answer in the chat box? Try to answer for this question. 32 and 64. Okay. Yeah. That is n is 16 the log base to 16. So 16 log base to, it can be written as 2 to the power 4, like, so log base to 2 will be 1. So 16 into 4. So how many? 64. So total 64 complex additions are required. Similarly, we will solve 16 by 2 log base to 16. So 8 log base to 2 to the power 4. So 8 into 4, that is 32. So total 64 complex additions and 32 complex multiplications are required. Okay, so option C is matching with this answer. So option C is the correct answer for this question. Okay, so moving to the next question. Now, next question is, for a decimation in time FFT algorithm, which of the following is true? Option A, both the input and output are in order. Option B, both input and output are bit reverse. Input is bit reverse and output is in order. Option D is input is in order and output is in bit reverse. So which one is the correct option? So it is DIT. That means decimation in time FFT algorithm. So already we have seen in the butterfly diagram, in the we are giving the inputs in the bit reverse order and output we are getting is in order. Okay, so DIT FFT algorithm processes the time domain input by dividing it into, that is x of n is there, we are just dividing into a two part, f1n and f2n. Okay, and then input sequence are rearranged in a bit reverse order. Okay, and output of the FFT computation is in normal order, that after performing the butterfly diagram already we have seen. So this is the even number of sequence f2n, and this one is in the, sorry, it is in the odd number of sequence, 2n plus 1. Okay, so option C is the correct answer. Input is in bit reverse and output is in order. Okay, so moving to the next question. Now next question is, the butterfly diagram as given in figure is used in the computation of, it is used for which one? Can you answer for the which FFT algorithm is it is following? Either decimation in time FFT or decimation in frequency FFT. Option C, all of the mentioned, or option D, none of the mentioned. Can you answer? It is for used for which one? Which one? Either DIT or DIF. So already we from here we can see that the input is in bit reverse order, bit reverse order and output is in sequence. Output is in sequence. Okay, 0, 1, 2, 3. So it follows the DIT FFT, decimation in time FFT, because in DIT we are giving out input is in bit reverse order and output is in order. So option A is the correct answer. So for that you just need to see the butterfly diagram, input and output. Okay, how they are managing. So option A is the correct answer for this question. Now moving to the next question. Now next question is, what is the sequence Yn that results from the use of 4-point DFTs if the impulse response h of n is given 1 to 3 and input response x of n is given 1 to 2n. So what will be the y of n they are asking. So it is a simple DFT problem. So from here there you can calculate it. Okay, so there are different ways you can calculate any of the ways. So I'm calculating the direct formula first, then we will reverse it. Okay, so already we know that the formula of the DFT, that is x of k is equal to n will vary n to n minus 1 x of n e to the power minus j 2 pi by n k n. Okay, and also I will suggest to please carry one calculator while solving this problem, because there are a lot of calculations are there in this lecture. So just carry one calculator to solve the problem. So already I have calculated the values, so I will write, you can calculate it separately. Okay, I will tell you how to calculate. Okay, so here, and also we, as we know that from the DFT properties, that is convolution in the time domain, that is x of n, convolution of h of n, there will be the multiplication in the time domain. Simple. Okay, so already this we know that x of k into h of k. So similarly here we will find h of k, frequency domain representation of this signal, and x of k, the frequency domain representation of x of n. Then we will just multiply. Then again we have to inverse DFT because we need a y of n. What will be the sequence of y of n? Okay, so already that we know that. So first let's solve the problem. Here h of n is given. First we will solve for h of n. Okay, first we will find out the h of k. So the DFT of h of, that is DFT of h of n, here we have to write h of n is h of k, which is equal to n is equal to 0 to, here it is a 4 points, here it is a 3 points, so here we will add a 0, we will add 1 0. So what will be the total sequence, because it must be a 4 point. Okay, so 1 to make a calculation easier, otherwise you can directly calculate here, because at the end it will be the 0 only. Okay, 0 to 3 n minus 1, so n is 4, because here it is given we will results will be use 4-point DFT, that's why we will add 1 0 here. So n minus 1 will be 3. Okay, here h of n e to the power minus j 2 pi by n is there, so 4-point DFT, so k into n. Now we will h of k, just open this summation, then we will n is equal to, when we will put n is equal to 0, So h of 0 e to the power 0. Okay, this part n is 0, so this part will be the 0 only. Now h of 1 e to the power minus j. Here 2 will, so pi by 2 will be there, only k, because n is equal to 1 will be there, plus h of 2 e to the power minus j pi by 2. So here n is equal to 2, so 2 into k, plus similarly h of 3 e to the power minus j pi by 2, 3 k will be there. Okay, so just I am removing some here. So I hope you have noted down. H of n is this. So now we will put the values of h of 0 is 1, h of 1 is 2, h of 3 is 3, and h of 4 is 0. Okay. So h of 0 is 1. Already we know that 1. So e to the power 0 will be 1. So 1 plus h of 1 is 2. So 2 e to the power minus j pi by 2. K values we will calculate one by one. Okay. Plus h of 2 is 3. So 3 e to the power minus j pi k, because 2 and 2 will be cancelled out here. Okay. Plus h of 3 is nothing, so it is 0. So this value will be 0. So this value we have got, h of k is equal to this one. Now similarly we have to calculate h of 0. Okay, what is the frequency domain representation of this signals? So if you simply put k is equal to 0, so e to the power 0, e to the power 0, so we will get here 1 plus 2 plus 3, so total 6. Okay, h of 0. Now similarly we have to calculate h of 1. So if you put k is equal to 1 in this equation, you will get 1 plus 2 into e to the power minus j pi by 2 plus e to the power minus j pi. Okay, because k is equal to 1. Here we are putting k is equal to 1. Now further if you calculate, you will get 1 into 2 e to the power minus j pi by 2. Value will be, what is the value? You can calculate. I have calculated, it is a minus j. Okay, you can calculate it. E to the power minus j pi by 2. You can directly calculate cos pi by 2 minus j sin pi by 2. Okay, so cos pi by 2 is 0. It is a sin pi by 2 is 1. Okay, so 1 minus j. So this way you can calculate it. Okay, similarly you have to calculate e to the power minus j pi. So this value is, if you calculate it, is minus 1. Okay, so 1 plus, sorry, minus 2j minus 3. So from here you will get minus 2 minus 2j, h of n you will get minus 2 minus 2j. So I am just writing the all values of h of k here, where k will vary 0 to, so here first one is 6, second one is minus 2 minus 2j, third value we will calculate. Okay, so I'm removing it from here. Just all those things you can calculate it separately. That's why I have told you to just carry one calculator. Now we have calculated h of 0, h of 1, now h of 2. Similarly, we have calculated h of 2. Now put k is equal to 2 in this equation. So 1 plus 2 e to the power minus j pi. Okay, so 2 and 2 will be the cancel out, that's why 2 pi plus 3 e to the power, that is we are taking k is equal to 2, so e to the power minus j 2 pi. Okay, now calculate e to the power minus j pi value and e to the power minus 2j pi value. So 1 into 2 for value e to the power minus j pi is minus 1 and plus 3 e to the power minus j 2 pi is 1. Okay, so from here you will get here, so minus 2, okay. So 2 you will get 2. Okay, so 2. Now similarly we have to calculate h of 3, so we will get 1 plus 2 e to the power minus 3 pi by 2, 3 pi by 2, it is j, plus 3 e to the power minus j, so 3 is there, right? So 3 pi, 3 pi. Now if you further you will find out the value, so you will get 1 plus j, the value is this, plus 3, the e to the power minus 3 j pi is minus 1. So from here you will get minus 2 plus 2j. Okay, minus 2 plus 2j. The fourth value is minus 2 plus 2j. So h of k we have got. Now we similarly we have to find out the x of n or x of k also. Okay, so now let's calculate x of k. Till now you can calculate using the same formula. Okay, so similarly we have to calculate x of n also. Okay, so this is a large task that will take some time, so please calculate parallelly, otherwise we would not able to complete. The x of k is equal to summation n will vary 0 to n minus 1 x of n e to the power minus j 2 pi by n k n. Okay, similarly, so n will vary from 0 to 3 x of n e to the power minus j 2 pi by 4 k n. Similarly, n is equal to 0 to 3 x of n e to the power minus j pi by 2 k n. Okay, so now we have to write in that form. Just open summation. So x of 0 e to the power 0 plus x of 1 e to the power minus j pi by 2 k value we will put later. Similarly, x of 2 e to the power minus j pi k plus x of 3 e to the power minus j pi by 2 k is, sorry, 3, the value is 3, so 3 k. Now we will put the values of k is equal to 0, 1, 2, 3. Then we will find out. So first we will find out x of 0. So here I am writing x of k first, just putting all these values. So here x of 0 is 1. So 1 plus x of 1 is 2, right? So 2 e to the power minus j pi by 2k plus 2, because x of 2 is 2, again e to the power minus j pi k plus x of 3 is 1. So e to the power minus j 3 pi by 2 k. Now we will put the values x of 0 first we will get. So here I am writing it directly, otherwise we could just put the k is equal to 0 value, and then we will get it 1 plus 2, because k is equal to 0, e to the power 0. So e to the power 0 will be 1. So 1 plus 2 plus 2 plus 1, we will get 6 again. So x of k, just we need to write the values of x of k. That is, first is 6, right? So now we will find out x of 1. So x of 1 will be 1 plus 2 e to the power minus j pi by 2 plus 2 e to the power minus j pi plus e to the power minus j 3 pi by 2. Okay, you will find out these values: e to the power minus j pi by 2, e to the power minus j pi, e to the power minus j 3 pi by 2. Already I have told you how to calculate. Okay, so here we will get 1 plus 2 minus j plus 2, here e to the power minus j pi by value is minus 1, plus that we will get j. Okay, so here you will get the whole value will be minus 1 minus j. Okay, so 2 1 minus 2 minus 1 and minus 2j plus j. So minus 1 minus j we will get. Similarly, we need to find out the value of x of 2. So 1 plus 2 into e to the power minus j, pi will be there, plus 2 e to the power minus j 2 pi plus e to the power minus j, I think for 3 pi will be there. Okay, because 2 will be cancelled out. So 1 plus 2 e to the power minus j pi value 1 plus 2, this value is 1 plus 1, and this value you will get minus 1. So that will be the cancel out, you will get 0. So 0. Okay, x of 2 value is 0. Similarly, you will get the x of 3 value. Okay, so when you will solve this, so x of 3 value you will get minus 1 plus j. You can check it, just oppose your that 1 plus j minus 1 plus j you will get. Okay, now we have got the x of k and h of k value. Simply multiply these, then take a inverse DFT. Okay, just I'm removing all those things so you can calculate it again. So I hope you have noted down, otherwise you can get it from the videos. So just a minute, my work got stuck. Yeah. So now just for y of k, it is a multiplication of h of k into x of k. Okay, so already we have got that. So just multiply these two. So what is the x of k? That is 6 minus 2 minus 2j, 2 minus 2 plus 2j. And another sequence is 6 minus 1 minus j, 0 minus 1 plus j. Okay, so it is at 0th position 1, 2, 3. Similarly here, so 0, 0 position, 1, 1 position and 2, 2 position, just multiply. So you will get 36, 6 into 6, 36. And if you just multiply minus 2, minus 2j, minus 1, minus j, you will get here 4j. And 0 into 2, 0 will be there. Similarly, if you multiply this one, you will get minus 4j. Okay, so this is a y of k you have got. Okay, now for getting the inverse y of n, just you have to do the inverse DFT. I DFT. So already we know that k will vary from 0 to n minus 1. Y of k, we have got e to the power j 2 pi by n, n k n. So n is equal to 4 because it is a 4-point DFT. K is vary 0 to 3. Y of k e to the power j, here pi by 2 will be there, into k into n. Okay, now if you open this one, you will get y of 0 e to the power 0 plus y of 1 e to the power j pi by 2 k, right? N is equal to 1, yeah, plus y of 2 e to the power j pi by 2 k into 2. So 2 2 will be the cancel out. Y of 3 e to the power j pi by 2 3 into k. Okay, now put all these values and calculate it. So you will get it like this. So 1 by 4, y of 0 is 36 plus y of 1 is 4j, right? 4j e to the power j pi by 2k plus y of 2 is 0, right? So this part will be the 0 plus y of 3 is minus 4j. So here will be the minus 4j e to the power j 3 pi by 2 into k will be there. Okay, now put the value of first, if this is a value of y of n, now put n is equal to 0, then 2, then 3, you will get the value. So y is equal to first putting 0. So if you put 0, so just what left, this part will be the 0 only. So 36 plus 4j minus 4j only left. So this will be cancelled out. You will get 1 by 4 into 36. So you will get 9. Okay, so y of n you will get 9. So now we will not require this part. So I'm just removing it so that we can. Okay, so all these parts are not required now. Oh, okay, that is required. Okay, that is fine. So I have So y of 0 we have got, that is 9. Okay, so y of n, so what we have got, 9. First value is 9. Now we will get the y of 1 also, just putting in this equation 1. So 1 by 4, 36 plus 4j e to the power, just put k is sorry, n here will be, because yeah, n will be there because k values we have put it already. So here y of 1, so n will be 1 only, so here plus, not a minus. Yeah, so j pi by 2 minus 4j e to the power j 3 pi by 2. So 1 by 4. Further, if you calculate it, you will get these values. So you will get mostly plus 4j. This value you will get j, and this value also you will get j. 1 is, I think, minus j. This one, and this will be the minus j will be there. Okay. So if you further do that, you will get 36. Here j square is minus 1, so minus 4. Here also, so minus minus plus, again j square is minus 4. So you will get 28 divided by 4. So you will get 7, right? Yeah, 7. Now similarly, you have to calculate y of 2, just putting n is equal to 2. So you will get 1 by 4, 36 plus 4j e to the power j pi minus 4j e to the power j pi 80. Okay, j 3 pi. Now further you will do that, you will get here j and j, you will get the value 9. Okay, because this will be the, this will cancelled out, so you will get 9. Again y of 3, similarly you will calculate 1 by 4, just putting n is equal to 3 in this equation. You will get 36 plus 4j e to the power j 3 pi by 2 minus 4j e to the power j 9 pi by 2. Now further if you do that calculation, you will get 11. Okay, so this sequence you will get 9 7 9 11, that is option D is the correct answer. Okay, I hope you have understand. Just find out the x of k and h of k, then multiply it, and again find out the inverse DFT. Okay. Okay, so now moving to the next question. Okay, so next question is n is equal to 88 point DFT is computed of a sequence x of n using divide and conquer approach, where n is equal to m into capital M into capital L, and m and L is also they have given. So given n is equal to 88 point DFT, and n is also given as m into L. So m here it is given 8 and L is given 11. Okay, for computation the sequence is stored in the two-dimensional array indexed M and L. If mapping is done this way, then how many rows and columns will be in the above two-dimensional array? Okay, they are saying that the mapping is done y capital M L plus M. Okay, so already we know that L is row index, capital L, sorry, small l is row index, and small m is column index. Okay, and this small l will vary L to L minus 1, that is that L is given 11, so that means it will vary to L is given 11, so 11 minus 1 is, that means 10. Similarly, the small m will vary to m minus 1, that means 0 to m capital, that is 8 is given to 7. Okay, so how many rows and columns will be there? So that is representing this L is, that is small l is represents the row index, so L is the 11, that means row is 11, and small m, sorry, capital M is equal to 8, that is column. Okay, so 11 rows and 8 column. So option A will be the correct answer for this question. Okay, okay, so I hope you have understand. So moving to the next question. Now next question is, if x of k is the DFT of x of n, which is defined as x of n is x1n plus j x2n, where n variable 0 to n minus 1, then DFT, what is the DFT of x1n? What is the DFT of x1n? Okay, so here it is given x of n is equal to x1n plus j x2n. Okay, and x1n, already we know that how we can get x1 xn plus x conjugate of n divided by 2, and similarly x2n, how we can get it? X of n minus x conjugate of n divided by 2j, because real and imaginary part. Okay, so this already we have seen in the first or second lectures, all those things. Now we need to find out the x1n. Okay, so this part, this one, so x2, and we didn't require, so I'm just removing it. So just we need to calculate. So just apply DFT in both sides. Apply DFT in both sides. Okay, so it is x1k, because DFT of x1n is x1k. Okay, so and DFT of xk plus x conjugate k, it will be n divided by 2, right? Now already we know that the properties of the DFT, the property of DFT is, that is x of k is equal to x conjugate of n minus k, that conjugate property we have seen that. Okay, so from here xk is equal to x, so just putting this property to here, so you will get x conjugate n minus k plus x conjugate of k divided by 2, or it can be written as 1 by 2 x conjugate of k plus x conjugate of n minus k. Okay, So from here we will get which option is correct. So 1 by 2 x conjugate k plus x conjugate n minus k. So option A is the correct answer for this question. Just putting this to here in this equation. Okay. From here we will get the value of x1 k, that is a DFT of x1 n. Okay. So moving to the next question. Now next question is, for computing 512 point DFT using decimating in time radix to FFT algorithm, determine the required number of complex additions. How many complex number of additions are required? So here it is n is equal to 512 is given. Now for DIT FFT, how many complex additions are required? DIT FFT, the number of complex addition is equal to, we know that is n log base to n. Okay, so n is given, that is 512. Sorry, 512 is not into log to 512, right? So 512 log base to 2 to the power how many times? 9 times. Log base to 2 will be the 1. So 512 into 9. If you further calculate it, you will get 4608. Okay, so option D is the correct answer for this question. Okay. Okay. So now moving to the next question. If xk is n by 2 point DFT of a sequence x of n, okay, where n is equal to 256, that means 256 point DFT is given. Then what is the value of xk plus 128? Okay, so xk is n point DFT, x of n is n point, and n is given as a 256. So what will be the 1 by 2? So 1 by 2 is 128 points. Okay, so that means it is dividing even and odd part. So 1 is even, 1 is odd. So then what is the value of xk? 128. So where f1k and f2k are the n by 2 point DFTs of f1 and f2n respectively. So that means similarly they are saying x of n is divided by 2 points, that is f1n, f2n, right? And their n by 2 point DFTs are f1k and f2k. Their DFT is given, DFT. Okay, corresponding the even numbered and odd numbered samples. This is even, this one is a odd number. So what will be the xk plus 128? Okay, so here, so as we know that xk is even and odd, it is divided. So f1k plus, already we know that the lower part is divided by the space factor, right? So this is f2k. We will solve one question or this justification in the later question. I have one question related to that. Just now you see that this is the basic thing. So this is given. Okay. So we will solve how it is related. The brief description, it is given in another question. So just you Just consider it. The xk is the this one, f1k plus wnk f2k. Okay, so this is a basically even and odd part. The lower part, that is odd part, is multiplied by this phase factor. Already we have seen in the butterfly diagram. Okay, now f1k and f2k are periodic. Already we know that, with period n by 2. f1k and f2k are periodic with period n by 2. Already we have seen the many DFT, in the DFT properties and many problems also, that periodic signal and periodicity property of DFT. So that will be applied same here. Okay, so f1 k plus 1 by 2, by the periodicity property, it will be the f1n, it must be equal to, right? And similarly for f2 k plus 1 by 2, it is not periodic, it will be the periodic with phase, with wn k, with this phase factor, that will be the periodic. Okay, now further we will solve it. Just a minute, I have to remove it from here. Okay, so we have seen till here. So if you further we will solve it, that will be the also periodic. We have seen that with this phase factor, so that will be applied here. Okay, n by 2, this in this one. So what will be the value? If you further just divide it, so you will get wn k into wn n by 2, right? That can be written like this. And if you further do that, so you will get, we can write it like n by 2 into n. This 2 will be, can be shifted from here to here, right? So now if you further do that, you will get minus wn k here. Okay, by shifting this phase, this periodicity property, if you applied here, so this will give this part. Okay, so and similarly f2k will be there here, this one, just because we are doing in this part. Okay, so by the applying the periodicity property, so you will get f1k will be the same, because there is a no phase shift, but in the f2k there is a phase shift, so this one will be applied here, f2k. So just we are solving this part only, here it is not required. So from here you will get it. Okay, so this one here, so already n is given, that is f1k minus, here just putting n, that point 256 k f2k. So you will get it. What will be the xk plus 128 value? So first 128 value will be the this one, and next 128 value will be the this one, equal to this one. So f1k minus w256n k. Okay, so option B is the correct answer for that question. Okay, so I hope you have understand this question how to solve, and this explanation I will give you in the next another question, that there is a one question. Okay, so just remember this one. So now moving to the next question. So next question is, the DFT of X signal X of n is computed using radix 2 FFT algorithm if the length of the DFT is 1124, that is just a minute. My pen stopped working. So okay. So here n is equal to given 1024. Okay. So here the length of the DFT. So how many butterfly computation process will required? So number of butterfly computation that is required, number of, sorry, my pen is just stopped working, so I'm not able to write. So just I'm trying. So total number of butterfly computation that is required. So total number of butterfly computation that is required for this process is equal to, there is a one formula for the vector algorithm, that is n by 2 into n. Okay. So n total number of, I have told you that is 8 point DFT, so 2 to the power 3. So n is the number of stages. Okay, it is a n is number of stages. Okay, number of stages here, that is. So how we will get it? 1024. How many times? So 2 to the power 10, right? So here n is equal to 10. Okay, so n is equal to, I am writing here 2 to the power n. So this n is the number of stages. Okay, so just putting this, so you will get 1024 divided by 2 into 10. Okay, so if you further do that, so you will get 512 into 10. So finally you will get 5120. Okay, so number of butterfly computation process will be required, that is 5120. Okay, so option A is the correct answer for this question. So now moving to the next question that I have told you, that is this question is there. Okay, but I will solve this question later because my pen is not working, so I will not able to write here. Okay, I will solve this problem in the later part. So till now we will do some another problem. Okay. Okay, so I will solve this problem in the later. First we will see some other problem where the less computation or something is required. So when my pen is start working, I will start. Okay. Okay. So there is another question. The question is, a designer has available a number of 8-point FFT chips. So explicitly how he should interconnect three chips, such chips in order to compute the 24-point TFT. So that means here n is given, that is n is equal to 24. Okay, it is a 24-point DFT. So now they have asked, a designer has available a number of 8-point DFT chips. Okay, so 8-point DFT chips are they have. So how many should they interconnect such a chips in order to compute? So how many? So 8 into 3. So that means 3 chips they are required. So 3 chips they should interconnect, so that 24 will be there. So 8, 8, 8. So total number of 8 points they already have. So that 8 point DFT they have to connect. So uh, so for that we have to create the three subsequences of 8 point each. Okay, so that 24 point DFT 0 to 24 till just we have to divide by a 3 each. So first what we will get 0, 3 in the each interval of 3, 9, then 12. So till first we have taken the 3 TFT point, that is first one, second one and 3 one, and each will be divided by interval of 3. Okay, so already we know that this is a basic formula of DFT y of k. So we have just divided that 24 point in the 3 subsequent points. Okay, because they have only 8 point DFT chips. So that 8 point DFT we have to connect the three interconnections will be there. Okay, so now just further rephrasing that, here n will vary 0, 3, 6 to till 21, and y of n w n kn, simple DFT formula, that three interconnections we have connected. Similarly here n will vary 1, 4, 7 till 22, again 2, 5, I mean every interval of 3. Okay, now the 3 interval, that means 3i, that can be written is here I is equal to 0 to 7. In this way that can be written this way, 3i w n by 3 ki. Similarly 3i plus 1, 3i plus 2, in that form. Okay, now already we have seen in the previously how we can solve it. So what we are doing, just I am taking just one example where we are taking y 3i plus 1. So here we are also adding in this form also, right? So w n k, because in the place of n, small n, we are putting this one. Okay, 3i plus 1. Okay, so 3i plus 1. So that will be the multiplied by this one, and this w n k into 3i. Just a minute, if I can write it. Oh, well, it started. Okay, so just why when we are putting 3i plus 1, similarly we are putting in place of n, so just putting, so w n, and here it is k, in place of n we are putting 3i plus 1, right? So w n 3 ki into w n kn, right? Kn, we can write it like this, kn not n, it is 1. So wn k, so wn k will remain same. Okay, and this part we can write it, if we take here ki into n by 3, we can write it into wn k. So we can write it like this. So this is similarly that way, similarly in this way also. So that will be the common here, wnk y2kn if you put in, and similarly wn2k y3k. So this way we can solve this problem. This they have said that so explicitly how he should interconnect three such chips in order to compute. So this way they can interconnect by this equation. So y1, y2, y3 represents the 8 point DFTs of the subsequences, and these are the phases. Okay, in y2 and y3. Okay, so just they have asked how. So here the solution is already given. Just I let you know. Now we will solve this problem. Okay, so already now. Okay, so here it is given if we split n point data point into two n by 2 point data sequences f1n. So n is given, which is a n point DFT. Okay, so already we know that endpoint DFT is divided into two parts and two data sequences, that is one F1 n and F2 n. It is a even numbered and this one is a odd numbered sample, and the DFT of F1 n is F1 k and DFT of that F2 that is F2 k. Okay, respectively it is given. Then what is a first n by 2 point DFT of xk of xn? So what will be the this DFT? So here already told you that is divided into two parts. So just simply first we will write the equation of the DFT, then we will solve. So already we know that F1, I can write it here, F1 is an even number, so that means x2m, right? And F2n is an odd number, so x we can write it 2m plus 1, right? F2n here, so it is can be written like this, and it is 1 by 2 1 by 2. So just I'm removing it from here so that I can write. So already we know that the equation of the DFT, that is xk is equal to summation n will vary 0 to n minus 1 x of n wn. I am writing in this form. So already we know that what is it, wn en, it is okay, already e to the power minus j 2 pi by n kn it can be written. So if we will divide this equation into even and odd numbers because xn we are dividing and xk is the DFT of xn. So here, so we can write it n even part, even number, so xn wn kn plus an odd numbers, whatever equation is number will be there, xn wn kn. Okay, so already f1 I can write it here, f1 f2, okay, because it is divided. Now in place of even number we can write it, I'm just taking m, so m will vary, m is equal to 0 to n by 2 minus 1, right? Because we have divided n by 2, n by 2, n by 2 minus 1. So here f1 x 2m we can write because it is even sequence. So wn 2km. Similarly for this one, m will be 0 to n by 2 minus 1 x 2m plus 1 multiplication wn k 2m plus 1, right? In place of n we are writing, because now if you further solve it, what you will get, okay, it is x, okay, so we can write it directly here. So if you further solve it, m will vary 0 to n minus 1 to x 2m w, if we will take n by 2 km, right? We can write it like this. Similarly here m will be vary 0 to n by 2 minus 1 x, or you can write it f2 n, we can write it here because it is equal. So x 2m plus 1, and further just we need to solve this phase. So wn k 2m into wn into k only, right? So this phase there is a no, because it is 2m plus 1, So now it can be written as like it is a DFT simple F1k plus just take it out WNK, right? WNK. So what is it? If you write it similarly in this way, you will get F2k, right? So they have also what is the first n by 2 point DFT. So this one is a first n by 2 point DFT. If you find out after n by 2, first n by 2, then next n by 2. So for next n by 2, already we know that in the butterfly diagram, we are just taking minus 1 here. So if you take that minus 1, so the next n by 2 point DFT will be the F1k minus WNK F2k. That equation we have taken from there. Okay. Okay. So this is the solution for this one. So I hope you have understood. So option C is the correct answer for that question. This question. So this is a proof of this one. Okay. Okay. So I hope you have understood. So moving to the next question, we have taken this one. Now next question is they have asked using the ITFFT compute DFT of x of n, that is x of n is given as cos n pi by 4, where n will vary 0 to n minus 1. So that means n is it is 8 point TFT, 8 point TFT. So already butterfly diagram has given, just we need to find out the values. Okay, so it is a cos x of n is equal to cos n pi by 4. Here n will vary 0 to 7. Okay, so just in order to find out the x of n, sequence of x of n, just we have to put the values of n. First n is equal to 0 till 7. Okay, if you put these values, so you will get cos 0, then if you put cos n is equal to 1, so you will get cos pi by 4, cos pi by 2, cos 3 pi by 4, cos 4 pi by 4, that is cos pi, then cos 5 pi by 4, then cos 6 pi by 4, and next cos 7 pi by 4. Just putting n value 0 to 7, then you will get the sequence. These are the sequences. Okay, just here we are putting. So these are the sequence we have got. If you further solve it, what is the value of cos 0 and this is all those things, you will get the sequence. Cos 0 will be 1. What is the value of cos pi by 4? That you will get 0.707. Next value is cos pi by 2, that is 0. Now next cos 3 pi by 4, you will get minus 0.707. And next value is you will get okay, I'm writing, you can calculate minus 1, then minus 0.707 again, then 0 again 0.707. Okay, so x of n sequence you have got this one. Now we have to divide it in the even and odd part. Okay, so I can write it like this. So I have less space. So if you rearrange this one, here x of okay, so x of 0, then we are because we are dividing f1 f2, then x of just mark it 0, x of 1 you will get 0.707, x of 2 you will get 0, x of 3 you will get minus 0.707, x of 4 you will get minus 1, x of 5 you will get minus 0.707, x of 6 you will get that is 0, and x of 7 you will get 0.707. So just putting, I'm calculating in the butterfly diagram, so you can just put all these values. So first one is 1, it is 1, not a 0. So 1, because x of 0, now we have to put x of 4 value because it is already given. So here minus 1. Now x of 2 is 0.707, x of 6 is 0. Okay, x of 1 is 0.707, x of 5 is minus 0.707, x of 3 is also minus 0.707, and x of 7 is 0.707. W, and here it is 8, so it will be the 0. Okay, so the value is 1. W80 value is 1. Okay, if you calculate it. Now this one is simple addition of these two values. Okay, so 1 and minus 1. So 1 minus 1 will be 0. Similarly here 1 is coming here, and minus 1 will be the plus, so it will be the 2, right? Again, so 0 here coming here, and 0.707, no, the value is 0 here. Yeah, something is wrong, it is 0. Yeah, x of 2, x of 2 is 0. So sorry, just be careful while solving this problem because it is here 0. Okay, so whatever you will add or do, you will get 0, 0, right? Now it is a 0.707 minus, here it is coming, so that is minus 0.707, so it will be also 0. Again it is coming 0.707, so minus, and this minus will be plus, so you will get 1.414. Okay, similarly here also it is 1 is minus, 1 is plus, so it will be the 0, and here 1.414. Okay, so these are the values you will get after stage 1. Okay, now after stage 2, how you can just group? Just simple add these two and minus these two in this. So it is 0, right? Yeah, 1 minus 1, yeah, it is 0. So here 0, and if you calculate W82, so it is e to the power minus j 2 pi by 8 into 2. So you will get e to the power minus j pi by 2. Okay, so what will be the value e to the power minus j pi by 2? E to the power minus j pi by 2, if you calculate, it is, I think, 0 cos. You can calculate it. Okay, first W80 will be the 1 only. So it is 1, it is, I think, minus j. Yeah, so it is 0. So here first 0 and next one is coming, that is also 0. Okay, if you multiply in this one, 0. So here again you will get 0. Next one is here 2. Now addition with this one, so here it is 0, so whatever will be coming, it is 2 only here. Similarly next one, here it is 0 coming, and here minus 1, so 0 will be there only, and here it is also 0 and it is 2, so 2 will be there only, right? Just addition and subtraction. Similarly here, if you do that, you will get 0 here, you will get here 1 point here, because W82 value is j. Okay, j. So you will get 1.414 plus j 1.414. Similarly, you will get 0 here. Here you will get 1.414 minus j 1.414. Okay. Similarly, you need to find the W18, W28 and W38 values and then just multiply and add in this. So x of 0 you will get finally 0. Here you will get 4. Here you will get 0, 0, 0, 0, 0 and 4. Okay. So DITFFT, whatever you will compute, the sequence you will get, that is 0, 4, 0, 0, 0, 0, 0 and 4. Okay. The DFT signal you will get that. The sequence is this one. Okay. So this way you can calculate and add it. Similarly, next question is related to TIF. Okay, here the sequence is given here. It is mistakenly it is 0. Okay, here input is in sequence and output is in reverse order. That means 2-point TIF. So x of n is given. That is here we can directly put it. Just a minute. So it is 2, 1, 2, 1, 1, 2, 1, 2. Okay. So here simple, it is a addition. So 2 plus 1, it is 3, right? Here it is 1 and here it is 2. So again it is 3. Similarly, you will get 3, 3 and here you will get just a minute. Here 2 minus 1. So here 1, right? Again here it is 1 minus 2. So minus 1 you will get here. Similarly here 2 minus 1, 1 minus 1. Okay. Now calculate W80, W81, W82, W83. Okay, values and then just multiply and multiply in this factor, then again do the calculations. So here it is 3, here it is given going 3 and here it is also going 3. Here no, so again simply add. Here also 3 and it is also 3, simply add. Here again, here 3 into minus 1, so minus 3 plus 3, 0 here, again 0 will be here. Okay, now calculate this one and multiply in this factor. So finally you will get here 12, 0, 0, 0, 1 plus j 0.414. Here you will get 1 minus j 2.414. Similarly, here you will get 1 minus j 0.414. Sorry, j, here you will get 2 point. 1 minus j 0.414. Okay, just calculate this phase factor and multiply. You will get, and then write it in the sequence 0, then 1. So the DIF x of n you will get from here, that is 12, then 1, 1 is 1 plus j 0.14, sorry 4, 1, 4 and then again 0, again 3 is 1 minus j 2.414, again 3, 4 is 0, then 1 plus, here it is 1 is plus, 1 is minus, here it is plus. Okay, so 5, 1 minus j 2.414, here it is plus. Similarly, 0, 1 minus J 0.414. So this sequence you will get. Okay. So moving to the next question because time is running. So if W 64, 16, this is equal, what will be the value of X? So it is simple problem. So if W 64, 16 is equal to W 128 to X. So just we have to keep these two same in order to find out. Okay. So can we write it like this? W 1, okay, 64 into 2 into X, right? We can write it like this, 16 into, yeah. Mm. So if you write, so 2x into 64, we can write here it is 64 into 16. So this n value is same. So directly we can, so just a minute, Wn 2k is equal to Wk n by 2. Okay, from there here you can write it. So 2x will be there. No, to make it equal. So here x we don't know. Just a minute. That x we don't know, right? So we can just multiply in this. We can so multiply by 2. In this equation we can put it like this one. So W 128 into 32 equal to, just multiply in this part, so you will get, right? So if you just compare it from here, you will directly calculate it, x is equal to 32. Okay, just we make this n is equal. So from there we can just compare it. Okay, so you will get C. Option C is the correct answer for this question. Okay. So now next question is calculate percentage of saving through Radix 2 FFT algorithm of DFT coefficients. Assume n is equal to 512. So how many percentage of saving the complexity? Okay. So here n is equal to 512 is given. Okay. So already we know that total number of complex multiplication in DFT. Complex multiplication in TFT is equal to n square, right? So that means 512 square. So if you do the calculation, you will get 262,144. Okay. So and number of complex multiplication using FFT, using FFT, so that is equal to n by 2 log base to n. So n is 512 divided by 2 log base to 512. If you further calculate it, you will get 256 into 9, that is equal to 2304. Okay, so percentage saving, how much percentage saving if you calculate it, that is 2604. 1 2 144 divided by 2304 into 100. If you calculate it, you will get 113.8. Just calculate it. Okay. If you calculate it, so option C is the correct answer. So just you have to calculate the total complex multiplication required in direct DFT and using FFT. Then calculate the percentage saving through TEDx to how much, that is 113.8. They are asking in percentage. Yeah, so just calculate it from here like this. Okay, so they have asked if x of k is the n by 2 point DFT of the sequence x of n, then what is the value of x k n by 2? Already we have solved this problem. I think it is similar to that one. So already we have seen that what is the value of x. Okay, so already as we know that we have already proved that as we know that x of k, the DFT is equal to in the even and odd parts f1k plus phase factor by f2k f2k and f1k and f2k is periodic by n by 2. K is periodic by with period n by 2. Okay, so f1k is equal to f1k plus n by 2 will be equal, but in the f2k, so f2k plus 1 by 2, but here the phase factor is there. In that case, f and k plus n by 2 will be there, right? So already we have solved. There is a 1 wn k factor will be there, and that is multiplied by minus 1. So if you further do that, f1k minus wnk f2k, from here you will get it. Okay, so x n plus k by 2, you will get this one, that is equal to b. Okay, now next question is, consider a 6-point decimation in time DIT FFT algorithm for which the signal flow graph of x1, we need to find for x1 only, is shown in figure 1. In this figure, let W6 is e to the power minus j 2 pi by 6. In the figure, what should be the value of coefficient a1, a2, a3 in terms of W6? Okay, so what will be the value we can obtain? So here these values are not given, so we will take just these values either, because they have not described this one also. So just we need to calculate this one. So what we will get here, this value x of 0 minus x of 3, right? X of 0 minus x of 3, right? Just add this, and that W6 0 will be there, but it is 1 only, so that can be a value 1, right? 1 a1 is equal to 1. Similarly, a2, what will be the value of a2? So this one sum and this one sum, and a2 will be the w6 multiplied by w61. Here w60, w61 and w62, because the 3 point, because here it is only 2 stage will be there. So in this stage we will multiply it by W62. Here it is multiplied by W60 before. Already we know that. So this value A2 will be the only this value because that values we don't know. So this is a 61 and A3 will be W62 because after this one we have to multiply this phase factor. So A1 will be the W60. So that is equal to 1. Okay. So A1 is equal to 1, A2 is equal to W61, A3 is equal to that is W62. So they are asking for because they have asked in terms of W6. So what will be the values? That is 1, W61 and W62. Okay. So option 3 is the correct answer. So I hope you have understand this question. Okay. So for today we have completed till this question. So anyone have any doubt, they can ask. Otherwise, we can close the session. Okay. We will solve this question in the next session because that is related to STFT and spectral diagram. So anyone have any question?
No, thanks, ma'am.
Okay. So okay, we can close this. So thank you everyone. Thank you for joining this session. Now you can leave the session if you don't have any doubt. Okay. So thank you everyone. Thank you for joining this session.